Good afternoon. How are you? We're back in the 10th and talking about um, gravity. In this case, though, what I want to talk about is uh, specifically black holes and the Planck limit. Now, the Planck limit itself, and I'll start with that, is in a nice, simple way that I'm capable of describing it, is the smallest measurement that we've been able to come up with as a calculation. Really, I mean, we haven't actually measured it physically, if you will. It is a mathematical calculation based on all sorts of elaborate reasoning, and it essentially is the very, very, very smallest um, unit of measure that we've come up with. Now, I've not heard anybody say that there's nothing below the Planck limit. Uh, it's implied, as far as I can tell, but simply we don't know. I don't subscribe to the notion that there is nothing below the Planck limit. There has to at least be gravity below that limit. But if you were a quanti thinker, in the sense that the universe is made up of discrete individual little elements, no matter how small, but there are recognizable discrete little elements that combine together into making something bigger, and then those combine into making something bigger until, you know, we're made, right? So atoms combine together to make other things bigger. Uh, if you're so quanti, if you're of that mindset, then there's a possibility that you'd think that once you get to the Planck limit, there's absolutely nothing below that. There's two reasons why I don't think that's the case. Uh, One, kind of fundamentally, is if there's absolutely nothing below the Planck limit, then I don't think the universe could exist to begin with, because if there's nothing underneath, to back up, the Planck limit is not site-specific, it's just a measurement. So you can measure anything, and down to the very finest level, down to the Planck limit, and it doesn't matter where you are or what you're measuring. So if there's nothing below the Planck limit, then there's nothing below everything. I know that sounds silly, but I think, though, that you couldn't have the universe starting from essentially nothing. Gravity has to be there, if nothing else. Now, the other kind of more concrete reason why I think there's something below the Planck limit is I believe you would be able to find or see um, larger representations of this nothing. Uh, if you think of water droplets on your window, and they individual drops, they get close together and they suck themselves together into a bigger drop, and then that gets into a bigger drop. If if there is essentially little pockets of nothing below the Planck limit, I would expect at least some of them to join together, to just kind of merge together into a bigger sphere, if you will, dimensional shape of some kind, larger area of nothing. So out in the universe someplace, we should be able to observe large areas where there's absolutely nothing, including gravity. That kind of brings me to black holes. Fundamentally, I think if you were to look for proof of the Planck limit, or at least a view of what it looks like, then inside a black hole is where you're going to find it. And I'll explain that now. With my view on gravity, it held together fairly well, except I couldn't fit black holes into it. I couldn't reason my way into figuring out why do we have black holes in my thinking. But then I read something that Professor Hawking suggested quite a while ago, I guess. And it was a notion that perhaps black holes evaporated. Now that stirred up a whole stink across the physics world, or physicist world, or whatever you want to call it. All the professionals got into a real tizzy about that, because the general notion is energy doesn't disappear. Everything that's in the universe remains here, and it doesn't go away. It doesn't disappear. It's often described just generally as information. So information does not disappear. In this case, energy is described as a type of information, which ultimately I guess it is. He recanted that later and said that it was, a pretty silly idea, and agreed that information, energy, doesn't leave the universe. Okay, that's fine. But that really set me off on a different path of looking at my problem with black holes. So, black holes don't evaporate. But perhaps they relax. And that's kind of my big step in explaining black holes. If you've seen an explosion on the ground, or the remains of it, a crater, you have a crater, and you have all the material on the edges, and there's this flat surface in the middle of where the explosion was, or it's a dip, right? I'm thinking that that's what's occurring in a way with a black hole. So I'm going to use my tinfoil prop again. All right. So no, it's not perfectly round like in the movies, and it is two-dimensional instead of being something else. But let's suppose, remember, this tinfoil represents the plane of our existence, or represents gravity. And in the center here is the black hole, what we call the black hole. So what I'm proposing is that an extraordinarily large explosion, a big star, flattens out gravity in the black hole. All right? And then all of the energy gets bunched up on the sides here. This is the event horizon, is a popular term for it. Now, all the rest of it is, the universe generally is just all bundled up tight like this, but right in the center here, in the center of the black hole, gravity is flat, and there's absolutely nothing else there. Right? There's no big mass in the center of a black hole, as far as I can tell. It's a flat, in my description, right? And it's a flat piece of gravity. So the explosion stretched out, took all the wrinkles out of gravity in that one particular spot. And in that spot is where you might find some sort of proof of the Planck limit. Except you're never going to get there. All right? So, this distance here, the flat distance in here, and I'm just using that, remember, I don't believe distance exists all by itself. It's a function of energy use. But the flat section of gravity here is so small, even if you could get past the event horizon, and I don't think you can, and I'll explain that in a second as well. Even if you can get past there, you'd pass across the flat part of gravity so fast you'd never know it, right? It's just so small. It would just go by without ever having noticed that you had, and you'd be winding up on the other side of the right back onto the on the event horizon. Now, why can't you get past the event horizon in my example? And let's go out to my drawing palette, and I'll explain what I'm thinking. I'll get back to you. All right, we're back. Let's see if this works. Might as well use my chainsaw file, since I have to file my chainsaw anyways in a minute. And here's my drawing palette. So let's see if it shows up. All right. Yeah, that shows up. Okay. This is a drawing of a NURB surface, or NURBS surface. I don't know if it's plural or not. If you're into CG stuff, computer-generated graphics, modeling, that sort of thing, you'll have heard the term of a NURB surface, a geometric surface. So, on a NURB surface, it doesn't matter how big it is. Your position is 0 at one side and 1 at the other. Same with this direction here. So 0 is down here and 1 is up here. Always. It doesn't matter how big this is or how small. All right. So now if you divide it in half, visually divide it in half like this, then this distance is 0.5. All right. Same on that side. All right. So there's half there, and there's the other half. So the distance here and the distance here is equal. Now I'm going to divide it up again. Oop, it's going to fall apart, I think. Yeah, no, there. All right, so I haven't visually divided it up evenly. However, something curious happens here. So I've divided into 4 pieces. And in a NURB surface, they're all the same distance. All right, so this is 0.25. That's 0.5 there. That's 0.75, and then 1 over here. Right? So they're all looked upon as the same distance. If you're familiar with topographical maps, they use this sort of method for showing vertical changes, right? A topographical map is a flat surface, and how do you show a vertical steep surface on a horizontal flat plane? Well, you put the lines closer together, because on a topographical map, all the lines are drawn the same distance apart. And it doesn't look that way on the map, but that's because you have changes in vertical distance as well. All right, so now I used this in my CG work, and it's a lot of fun to use this. If I want to simulate snow blowing across a surface or sand blowing across a surface, what I could do is I could actually draw lines. These are called isoparms in NURBS parlance, but I could draw essentially speed lines on my NURBS surface, and then when I put a force on particles that go across the surface, because these lines are thought of as equal distance, then the particle would actually go slower across this part and then speed up going across here. Right? So if I have a constant force going on them, then they slow down here and then zoop, it speeds up across the this distance, because this distance in NURBS is equal to these three distances. So that was really handy. All right, what's that got to do with black holes? Well, let's try another. There's my black hole there. And then we have lines and lines and lines of, in this case, NURBS lines, all the same distance. And you have, and all the energy is bunched up in here, right? So this is the plane of gravity, and it's all bunched up here, and it's holding all the energy that was in the star, essentially, all bunched up on the side here. But that also means that there's a great deal more distance here. Or if you want, you can say you have to use a hell of a lot of energy to get across here, and then once you get past the event horizon, you go across here, where there's essentially no energy and a flat plane of gravity, and it's extremely, what I would regard as extremely short. So that helped me a great deal in explaining what a black hole really is. Right. So remedial geometry. Back into my tinfoil example again. So I said instead of evaporating, the black hole relaxes. So what I mean is that the very, very simple area in here, and then the very intense area here on the event horizon, can't stay that way forever. And what I'm suggesting is that eventually the center is reclaimed and the event horizon relaxes, and it turns back into essentially normal space. The center here may collect, I would assume, most of that energy that was on the event horizon would collect in the center and form another star, perhaps. That kind of depends on how long it takes for the area to relax and how much energy was lost in the explosion, not to be recovered or not to be included in the event horizon, and then how long it took actually for the black hole to relax, how much energy was lost as the event horizon is radiating energy. So how much energy is left is going to determine what might form in that spot. A smaller star, a red dwarf, brown dwarf, who knows? I would think, though, that you might be able to distinguish um, between, what am I saying? Uh, I would think you would be able to see evidence of a spot, a star or whatever that was formed from the energy of a black hole that has relaxed. Maybe. Perhaps the universe isn't old enough yet for a black hole to actually relax to that point. I have no idea how long that might take. I'm sure there's all sorts of very wise and learned physicists out there that could probably figure that out if my crackpot idea is even worth considering. But you're going to be stuck listening to this idea for quite a while, so we'll continue.